Is this okay? Shirt. Pick in the middle here on your t-shirt. Is this okay? Not good enough. I will put it in the middle here. There, yeah. Sorry. Is this good enough? Yeah, I think that's over. Practicing. Oh, sorry.
All right. We start the last session, the last talk of this session, and we have Jiayu Zhang about succinct blind quantum computation using a random oracle. Maybe you want to remove the Zoom picture. Yeah, good.
Hello everyone. I'm very happy to give this talk on my result, succinct blind quantum computation using a random oracle. So I'm Jiayu from Caltech, and previously in BU. Not good enough. Okay. Thank you. So what is blind quantum computation? It's this problem, and it has a quantum circuit C and a quantum input phi. And you want to evaluate it and get C phi instead. Is this okay? But it doesn't have the ability to apply C itself, maybe because it doesn't have a powerful enough quantum computers. So it wants to make use of a remote quantum server. But on the other hand, it doesn't trust the server and want to keep this secret. So it wants to design a protocol to interact with the server and get the result in the end. And this is a very fundamental problem in quantum cryptography. On the one hand, the problem itself is very important in practice, because with high probability in the near future, quantum computers can only be used as a cloud service. So if some user want to make use of its power, and simultaneously, it want to keep its data or circuit secure, such a protocol is needed. What's more, the study of these problems has often led to new techniques that can be later applied in related problems, like quantum computation verification, which is a very fundamental problem in quantum computation and cryptography. So this talk will slightly simplify the problem by taking the initial state as a zero stream, and the only input to the protocol is the circuit size, is the circuit C. So what does blindness means? In this work, we formalize the blindness using a basic notion in cryptography called indistinguishability. It means for any malicious adversary, its viewpoint, the following two cases will be indistinguishable. And the first case is the real execution, where the client simply uses a real input as an input. And in the second case, there's nothing about the circuit C except its length, which means the adversary could not get anything about the circuit C efficiently except its length. So we only care about privacy in this work, where privacy is just means blindness, and we do not care about verifiability of the final result. So there are many existing works in this problem. Existing work can be classified into two classes. One class of protocol is IT-scale protocols. For example, the protocols by Broadband Basement Cachefi. And in this protocol, the client-side quantum computation could be only single qubit state. But the client needs to do many client-side quantum computations, which is linear to the circuit size C. And this is a big burden for in practice. Another class of protocols are protocols based on linear zero assumptions. like the protocols given by Mahathir 5 years ago. In this protocol, the client could be completely classical for classical input and output. So we can classify existing works into these tables, which show different relations between assumptions and resources in terms of client-side quantum computation. The BFK protocol is on the bottom left corner, and the Mahathir's protocol is on the top right corner, which means for existing protocols, we require either strong assumptions like learning with errors, or lots of quantum computing for the client. And let's go back to the existing work and focus on assumptions. Here, learning with error is a public key assumptions. And this protocol relies on learning with error because they rely on some primitives that are only known to be essentiable from learning with errors. So what if learning with error is broken? And could we design protocols that can be constructed from that has many possible instantiations? For example, we ask the following question. So what if we only have symmetrically cryptographic primitives? In cryptography, we can instantiate symmetrically primitives in many different ways, like AES or different hash functions. There are many possible instantiations in practice. And certainly for these problems, we have a specific goal, which is to make client-side quantum computations and communication to be independent of the circuit size C. Which means our protocol should be better than existing IT-scale protocols in terms of client-side quantum computations. And in this work, we work on the ideal model of symmetric primitives, which is a random oracle model. So what is a quantum random oracle model? This model is raised in this paper as a quantum generalization of the classical random oracle model. In this model, there's a global oracle, which encodes a random mapping. All the parties can query this oracle. And for the same input, the oracle will return the same random strings. And for different inputs, the oracle will return independently random strings. This is the ideal model for head functions or symmetric encryptions. We can design protocols in this model and prove the security. And in practice, we can instantiate the random oracle with head functions or block cipher and claim the security heuristically by random oracle methodology. So on the one hand, there do exist some instantiable constructions, like the constructions given in these papers. The security claim is ultimately heuristic. But on the other hand, quantum random oracle model and classical random oracle model have been extensively studied and provide some only known constructions of many cryptographic protocols in practice. So in this model, we give our work as follows. We construct a new blind quantum computation protocol, which is skilled in the quantum random oracle model. And the client-side quantum computation is only polycappa, which is independent of the circuit C. So in the details, our protocol has the following structure. First, the client will send some quantum gadget to the server. And this gadget can be prepared using only polycappa gates and is independent to the circuit C. Then both parties use some classical interactions to complete the protocol, and the client will get the result in the end. And our construction could be further divided into these two phases. The first phase is a protocol called remote gadget preparation. In this step, we design a protocol that can securely prepare many evaluation gadgets on the server side, where many means the number of gadgets should be linear in the circuit side C. And in the second phase, both parties do some classic gadget city evaluation protocols from the evaluation gadgets coming from the first step. And this step is based on existing works, which mainly is a BFK protocol. So the gadgets that we were using in this paper is of the following form. The client will hold two different strings as the keys, and the server will hold the superposition of these two keys as a gadget. So we can imagine the server can do a computational measurement and get one of the keys, but it has no ability to get both simultaneously. And this gadget is used previously by some existing works like this paper. So our remote gadget preparation protocol will be as follows. The client will first prepare and send some quantum gadget to the server, and he knows the keys. But the number gadget is not big enough for gadget city evaluation directly. So both parties use some classical interactions to expand the number of gadget to a large enough number. And in the end of the remote gadget preparation step, there should be two requirements. For the correctness, the client should get all the keys for each I, where I is from a large enough domain. And the only server should get the corresponding gadget, which is the superposition of these two keys. And for security, we require that for any malicious server and many key pair in index I, the connection of x0i and x1i should be unpredictable, which means the server could not get both keys simultaneously. And this is the most trivial part of our work. And we design the protocols using the following two steps. We first design a weakly secure protocol that can increase the number of gadgets. And then we amplify the security to get a fully secure protocol. Here, weakly secure means we allow the attacker to predict x0i concatenate x1i with some noticeable probability. But the probability should not be too big to make the security amplification unusable. So today I will give a toy protocol which illustrates how to create one new weakly secure gadget. So our goal is as follows. Initially, the server will host one gadget, x0 plus x1, and the client will know the keys. And the client wants to use some way to allow the server to create two gadgets on its side. And the output could have some weak security. To achieve this goal, we introduce the following ideas. We will introduce a reversible lookup table, and we introduce bitwise computation, a hammer test, and helper gadget. In this talk, I will focus on the first idea, the construction reversible lookup table for this problem. So gobble table or lookup table is a variation construction in classical word. And we can use this construction to allow the server to map input keys to output keys. As a simple example, if the input keys are x0 and x1, and the corresponding output keys are y0 and y1, we can define the gobble table as an encryption of y1 and x1, and encryption of y0 and x0. And this could be denoted in our work by the following simplified notion, x0 to y0 and x1 to y1. So why could we use this notion? That's because intuitively, if the server holds a table above, and if the server additionally knows one of the input keys, it could try to decrypt each row of the table, where each encryption is called a row of the table, and get exactly one of the output keys in this decryption process. So this is very useful in classical world, and we wonder whether it's possible to use this construction on the transformation of quantum gadgets. But unluckily, it's not compatible with quantum states. We can use this construction to map the superposition of x0 plus x1 to the entanglement of the input keys, output keys. But what we can do next? What we want actually is a superposition of the output keys y0 plus y1. But the plain lookup table could not do that because quantum operations should be reversible, but plain gobble tables and these evaluation circuits are not. So we use an idea from this paper we use a construction of reversible lookup tables. And this construction will contain two tables. In the forward table, it encodes the mapping from input keys to output keys. And in the backward table, it encodes the mapping from output keys to input keys. And the overall evaluation will be reversible. And we can use it to transform the input gadget to output gadgets. So the transformation will first decrypt the forward table and get the entanglement of input keys, output keys, and then it decrypts the backward table. And for this step, we will directly write the decryption result to the first register, and the input keys will be raised. So the final outcome will be simply the output gadget, which is what we want. And we can do some further generalization on this construction. For example, if the input case has 4 terms and corresponding output case has 4 terms, we can construct a reversible table that contains 4 rows. And we can still do the reversible mapping between input gadget and output gadget as long as the input key number is equal to the output key number. And we can further generalize this construction. For example, if the input gadget is a tensor product of 2 different gadgets, we can construct a reversible table that takes it to 2 output gadgets in a collective way. And each row of the reversible table will encode a reversible mapping from the concatenation of the 2 input keys and the concatenation to the 2 output keys. So we will use this construction in our work. So let's go back to our problems. So it seems that the input key number and output key number are not compatible. The input only has 1 gadget, and the output has 2 gadgets, which correspond to 4 components if we expand it on the computational basis. So to complete the construction, the first step, the client will sample a new key pair. And it will simply give this classical decryption to the server. So this step will not introduce extra client-side quantum computation because everything is done classically on the client side. And the server could prepare the key superposition from this new key pair from its classical description. So there are 2 gadgets here, and the client will send a reversible lookup table that encodes the mapping from the input keys to output keys. And the server can use the transformation that we discussed previously to get the corresponding output keys. And in this way, we complete the construction for the honest behavior. But suddenly, the client reveals too much information about the input keys, because one of the input keys are given simply classically to the server, and the output has no security or even weak security. And to rescue the security, we introduce the following 2 ideas in the paper. And in the end, we get 2 round protocols that allow us to create 1 more gadget, and output gadgets will have weak security. So in summary, we construct a protocol that is good in the quantum random oracle model, and the client-side quantum computation is only Polycarp, which is independent to the circuit side C. Thank you very much.
Right, thank you. Any questions? Everybody longing for coffee. I have 1 question. So in this table, you show like, I was wondering like how succinct it is, but you say it's independent of the circuit size.
Yeah.
Is this kind of the best you can get? Is this kind of optimal in a sense?
Optimal? Do you mean you want to solve the problem that is about this cell? well, the concept of quantum computation is classical and
Sorry, can you use your microphone and speak into it?
Oh.
Just take it off your shirt.
so certainly we can ask the question about whether we can construct a protocol that only use a classical kind and is secure in the quantum random numerical model. But I have no idea, and it's a very difficult problem in my opinion. But political pi is certainly much smaller than linear.
Yeah. Okay, thank you. I guess there's no more questions, so thank you for your talk. Okay. Let's thank all speakers of this session. I think we're having a break now for 20 minutes or so. Thanks.